Yeah, hello. I'm Jan from University of Heriot-Watt University in Edinburgh. And so, first of all, what are we talking today? What is amortized complexity? So if we take a simple stack data structure, we have a pointer to the top. We can only access the topmost element at any time. We can define it in Haskell. It's isomorphic to the normal list. And we will give this stack a push operation, so we can push a single element to the top of the stack. And in Haskell, this turns out to just be the LM constructor. So, but now instead of giving it just a pop operation which reverses the push, we will give it actually a multi-pop operation where you specify a k, and it will pop the top k elements from that stack. In this case, we just chose 3. Implementing that in Haskell, again, is not hard. We just recurse as long as we need to hit either an empty stack or we are done with how many elements we wanted to pop. But let's look at the timing or the complexity of these two functions. So push is obviously constant. We are just allocating a new cell, updating some pointers. It doesn't matter how little big the rest of the stack already is. However, the worst case for multipop is that we pop the whole stack. So the worst case of multipop is O of n. However, that's a little bit silly because after we popped all elements, we will not be able to pop all elements again. So it's technically the worst case, but if you look over like in a real execution, that doesn't really work out. So the key insight here is that, well, at some point to pop an element, we have to push it first. So instead of just looking at the single worst case for any operation, we look at over a sequence of operations, then look what will the worst case be. But important, we are still looking at the worst case. This is not like a probabilistic average case. This is still the worst case that can happen over a series of operations. So how can we reason about it? So there's 2 methods basically. There's the banker's method, and the idea here is we keep a bank account of time tokens that we can pay into in this account, or we can withdraw from the account. And so at the beginning we start with an empty stack, and our bank account is also empty. And when we push now, we not only pay, as a push we said costs 1 time unit because it's constant time, but we also make it pay an additional time unit into the bank account. So after this 1 push, we end up with a stack that has 1 element, but also we have now our time token saved up in our bank account. And we can repeat this a bunch of time, and this new push operation is more expensive now, but it's only a constant factor. Our push operation is still a constant time. It just costs 2 instead of 1 time tokens now. But the interesting thing now is we always have as many time tokens in our bank account as there are elements on the stack. So once we do our multipop operation, we can use our bank account to pay for that expensive operation. So now the cost of multipop is amortized 0 because we pay completely from the bank account for it. So now we say, well, the worst case of multipop is linear, but amortized, it is constant. And that's the basic idea between amortized analysis. Not every data structure has something like where the amortized complexity is better than the worst case complexity, but many interesting functional data structures do. So the problem with this bank account method, it's very hard to formalize because this bank account acts basically as a local state between all of these operations. So there's a better way to reason about this formally. So the idea here is we define some potential function. It will map every state of the data structure to a number, which can be anything. It usually will mean something how costly that state of the data structure will be for our operation. And then the difference in potential at every step, that will be our amortized complexity. So what does this mean? It means we will basically use this equation to calculate our amortized complexity, which is composed of the actual time it takes to do the operation. So that's 1 for the push operation in any cases, but for multipop it might be different. Then it's the potential after we do the operation minus the potential before we do the operation. So that's exactly this difference in potential that we will use to specify the complexity. So we define this potential function ourselves when we do the proof. There's two conditions on that. For any state of the data structure, we are not allowed to have a negative potential. Like the potential is always positive or zero. The other thing is an empty data structure should have the empty, like a zero potential. Yeah. So why is this a valid way to see amortized complexity? So if you look at a sequence of operation, 1, 2, up to n, we can notice that, well, those two cancel out in that equation. And not only those two, but basically all the intermediate things cancel out. So what we are left with is just all the actual time we spent on this sequence of operations, plus the final potential minus the initial potential. But as we said, by definition, the initial potential is zero, so we can get rid of that. And also we said that any potential is not negative. So this is only ever an over-approximation of the actual runtime of our system, never an under-approximation. So we can use this as an upper bound on the runtime. So we had a keynote already about this yesterday, but LiquidHaskell is a refinement type checker that allows us to specify extra properties on normal Haskell types. And it works by translating Haskell, or more specifically core, to the logic of an SMT solver, and then use that SMT solver to check those refinements. And it usually uses Z3. And for a few years now, it's implemented as a GHG type checker plugin, which makes it a lot more usable than it was before. And also nicely integrates with tooling like Haskell language server. So if we look at our definition of the stack and the multi-pop operation again, we want to prove now that this amortized complexity holds. So first of all, let's add a precondition to our multi-pop, because actually at the moment, multi-pop doesn't do the right thing. Because if you supply a negative number, which int does allow, we will just pop the whole stack, which is not what you would expect. So we specify a LiquidHaskell annotation that says, okay, we want an integer that is greater or equal to 0. We could also specify a post condition to specify functional correctness, that the list and the stack together have the length of the incoming stack, but we're not dealing with functional correctness today, we are only dealing with complexity. But now there's one issue. So for reasoning about the complexity, we will need to know how long a certain operation takes. We need this T actual. And for this, we need to derive a timing function, it's called, from our operation. And that basically follows the recursive structure of the program. So we take all the arguments of the original function and just replace the return type with an integer. And in fact, we replace it with an integer that is bigger than 0, because we always do some work. So at least we return a one-time token that it will take. And in the base cases, so if there is no function call on the right-hand side of our equality, we just replace it with a constant 1. So there's only data constructors and variables on those two right-hand sides, so that's fine. In the recursive case, we replace the recursive call by the timing function and then increment the result. So we also do more work. This transformation could be implemented with, for example, template Haskell, or probably nicer, a GHG source plugin. However, I have not done that as part of the Perl.
What about laziness?
I mean, the laziness stays the same between both of them. So we as you see, the case match, like we only increment after evaluation. But also LiquidHaskell uses a termination checker and reasons that if the function terminates, lazy programs and strict programs result in the same result. So to actually use these later on in our proofs, we will also need to reflect them into the logic of the SMT solver. So that way we can use those functions which are more complex than measures which LiquidHaskell automatically can use in refinements to also be able to use arbitrary Haskell functions in refinements. However, we will have to prove any properties about these functions ourselves. So how can we prove with LiquidHaskell at all? I mean, we saw pre and post conditions, but how do we actually do proofs? Nikki and others that are in this room wrote this paper a while back, theorem proving for all. And it basically added a few proof combinators to LiquidHaskell that help with that. So a proof is just unit, and in fact it's unit refined with the property we want to prove. So if the property is true, it is just unit, because anything refined with true is the original type. However, if the property is not true, it's unit refined with false, which is a type error in LiquidHaskell. Also, the other bit that makes this work is this triple equalities operator. And in fact, it's the refinement on that triple equalities operator that help us with the proof, because it asserts that in the logic of the SMT solver, both arguments are the same, and it will return a third thing, which is again the same as the first two arguments. So that way we get this equality rewriting going on, because at every step where we use this equality operator, the SMT solver will check that the left and the right hand side are really equal up to the logic of whatever logic we are working in. There's also some other helper function. I won't go into the definition in detail. This question mark operator can be used to bring facts into scope. So facts in LiquidHaskell are again just Haskell terms that have a refinement. So if you want to bring a refinement into scope, you can use the question mark operator with whatever term has the refinement. And triple star and QED are used to finish up a proof to make it look nice. So going back to our goal, we want to prove the amortized complexity. And as I said, we need to define a potential for our data structure that fulfills these conditions. And for our stack, we will just use the height of the stack as a potential, because the higher the stack, the more we will need to pay for multipop. That's the intuition behind that. And then our LiquidHaskell proof is just a function that returns a proof. And in this case, what should we prove? We should prove exactly the inequality what we had before that. This equation where the timing of the operation plus the potential after the operation minus the potential before the operation is less than or equal to some constant. I chose 2. Actually, in this case, I could have chosen 1. It doesn't matter, as long as it's a constant. Proofs in LiquidHaskell we can do by pattern matching, which is the same as case matching in the proof language. So we pattern match on the 2 base cases, and we write out our left-hand side of the equality, and we will do equational rewriting steps until we are at the right-hand side of our inequality. So writing out the left-hand side, then let's remember what these definitions are for this specific case. We can substitute all of those definitions in our term. Let's evaluate second as well. These 2 potentials cancel out, so we end up with 1. 1 is indeed less than 2, so that is the proof finished. This whole process is a bit tedious because, yeah, for this base case, it's obvious that this is a constant. It just doesn't do anything interesting. So LiquidHaskell comes with something called proof by logical evaluation, and you can enable this with a flag, either in your file or in your Cabal file. And you can also use this automatic instances annotation that says basically, okay, for this specific function, which in our case is a proof, any function inside it unfolded more than once. Because what we did here, we only unfolded all our definition 1 level in every equational step, which is by default enabled. But if we want to unfold more than once in 1 step, then we need to enable this. There's also a global PLE flag that does that for all functions. But I like it to just do it for the proofs where I need it. And with that enabled, the proof is actually trivial. And as we've seen earlier, trivial is just a synonym for unit. And unit refined with true is true, but the theorem prover needs to see that indeed the refinement is true. In this case, it can do so automatically. In fact, also the other base case is trivial. And not only that, but if you specify the induction, it can also do the complicated case. But let's look at that more interesting case a bit more in detail. So as we did with at the beginning, we can write out our left-hand side and remember what all of these things are defined for these cases. Do some evaluation of 1 step, and now we see the ones cancel out in this equation. So let's do that. And now we're left with something that looks suspiciously like our refinement in the first place. So we have multipop of n minus 1 and a potential of, again, n minus 1 and s minus potential of s that looks exactly like our refinement where we have k be n minus 1, which is a smaller term than what we started with. So we can use a recursive call, which in LiquidHaskell amounts to induction. So we bring this induction into scope with the question mark operator by calling our recursive function and thus bringing its refinement into scope. And because this proof terminates, this is an induction, a proof by induction. So for more complicated data structures, there will be more reasoning sets. But in this simple case, as I showed earlier, LiquidHaskell can do all the reasoning except for the induction automatically. So in the actual paper, there's a little bit more I talk about. So more interesting data structures than just the simple stack. So binomial heaps are this data structure where the children are, they are ranked, and every rank has all the previous ranks as its children. And a heap is a forest of those trees, and inserting into that is also amortized constant time. And it turns out that this proof is the same proof as you would have for a simple binary counter, so where you usually just flip a 0 to a 1, but if you have all ones, you need to flip all of them back to 0 and add a new 1 at the end. So that's the same complexity argument actually that you have for these binomial heaps. And then to go to the more complicated end of the spectrum with finger trees, cons and snock for finger trees, so adding an element on either side or removing an element on either side of a finger tree, like defined in data.seek, is constant time amortized. And so the implementation of finger trees that I chose to formalize is not actually the one from containers, but the one that was presented a few years back that is simplified. The main reason for this is that so the proof works the same way for the cons and snock case, even for the containers package. The problem is I also prove concatenation, which has logarithmic time complexity. So it also works with more interesting time complexities than just constant time. The problem with concatenation in the containers package is that it is implemented as two sets of 4 mutually recursive functions that do deep pattern matches. So they pattern match on more than one constructor level at once. LiquidHaskell needs to expand all of these pattern matches into fully disjoint pattern matches, which just blows up the number of constraints the SMT solver has to solve, which brings my PC to its knees. So the version by Kuhn doesn't have this problem. And in fact, it's very nice to implement with LiquidHaskell because a lot of the internal machinery of this implementation has some pre and post conditions on the functions, which you can directly, again, specify with LiquidHaskell and use those refinements then in your proofs. So that works out quite nicely. One of the big limitations of using the physicist method is this only applies in a linear setting, and that's in the linear Haskell sense of linear. So you're not allowed to reuse intermediate data structures. The reason should be quite obvious. So if I have a stack and I multipop it, but I reuse the original stack, I can just multipop again and again and again and never pay for this expensive operation. Some data structures can exploit laziness to do so. For example, finger trees also have these complexity bounds in a persistent case. So if you do reuse intermediate data structures by exploiting the memoization of laziness. However, at this very ICFP, there was a paper proposing a reverse physicist's method that could be used to deal with this issue, but that is still future work. Also, as I said, I currently don't have a way to define these timing functions automatically, but I've done some experiments, and it should be doable with, for example, a GHG source plugin. Sadly, template Haskell has some limitations that would make it very hard to do it with template Haskell, but a source plugin should work fine. As I also mentioned, deeply nested pattern matches need to be expanded fully, which causes an explosion of constraints for the SMT solver, and depending on the complexity of the program, might be too many constraints for the SMT solver. And the last bit, when developing the proof, it's really hard to see what is an error. So if you do a small error in any of those equational steps, you will see where the error is, but the error message itself is quite inscrutable. But then looking at the equational steps again, you usually see what's going on. And the last bit, so the implementation of the binomial heap, there is a very nice implementation that uses data kinds and type families to ensure functional correctness of these these heaps, and ensure that binomial trees are really binomial trees because they have a very specific structure. However, that clashes with the refinements of LiquidHaskell at the moment, but that's just an engineering problem, not a fundamental limitation. So in summary, in addition to functional correctness that we can prove with LiquidHaskell, we can also prove time complexity bounds on our operations. Using the physicist method compared to the banker's method makes it easy for formalization, and this approach scales to pretty much any complicated data structure like finger trees, with the small asterisk if it uses too many pattern matches. And as I said, future work needed for persistent data structure so that you still have these guarantees in the persistent case. Thank you.
Hi, thanks for the talk, very interesting. I wonder if you could tell us about how much cost does it have to do this kind of analysis? So you said when you try the seek, the depth seek,
yeah.
the data seek version, your PC couldn't handle it. But the case that did work with finger trees, how much memory, time does it need to actually verify something like this?
So even the simplified version, so the thing is, SMT solvers are very good at solving linear arithmetic. So plus, minus, so yep. Everything that will be a constant time is instant. So all of these examples, binomial heaps, the stack, no problem, cons, snock, all are instant basically from type checking perspective. The logarithmic proof is a bit more involved and also involves nonlinear steps. So this set3 has limited support for multiplication with a constant. It does not have support for multiplication between variables, but multiplication with a constant is fine. But even then, this generates 1,800 constraints for the SMT solver, which takes about a minute and a half to type check this proof. Which is not bad in general. However, if you develop the proof, you have this 1 minute type checking time basically after like 2 steps of reasoning, and then you add another step, you check if you still are type checking, add another step, and so that slows down your development time. So I'm not actually sure if I could complete the proof for the data.seek version, because it took 5 minutes at that point to type check, and I couldn't do it.
Okay, thanks.
Hi, I'm Laura Israel from Portland State University. I wanted to know if you have any data structures that you wish you could have included in your paper that didn't quite make it or it didn't work out with the system. I'd just like to hear about that.
No, not really. So I was looking for, so the thing is, this is in Haskell, so I was using for looking at functional data structures. For imperative languages, there's like growing arrays, which is a very nice amortized data structure. However, implementing them in Haskell is quite messy. So I picked from the functional subset of data structures, I picked the ones that are interesting. I thought I wanted something on the simple side, which is the stack, which, by the way, happens to be basically half of Okazaki's queues. And on the other side of the spectrum, I then picked finger trees because that's the most complicated functional data structure I know, and then I wanted something in the middle to balance it out. So I don't really have anything I didn't use.
Thank you.
So I guess I have 2 questions. The first one is, can you always define the potential just in terms of the data structure, or do you ever need to carry around like extra like meta?
No, the potential has to be defined only by the data structure. So in case of finger trees, for example, a finger tree has a digit on either side, and they can be between 1 and 4, or in the paper between 1 and 3. And the dangerous case is if they are either 1 or 3, because for 1, if you uncons, you need to recurse, and for 3, if you cons, you need to recurse. So the potential of finger trees is actually the 1 if it's either 1 or 3, and then plus the spine. So you never need to go outside the data structure, even for complicated ones.
Okay, thanks. My other question was going to be, so can this work with stref based, like if you have some impure data structure, because it sounds like the cost model is just, you just have this separate function, and that of course would be pure, even if the actual manipulation lives in ST. So would that work? Like if you wanted like some ST-ref based union find or whatever.
I think it should work. So you just need a way to define what is the potential before and after. So but if you have like a state token, you can thread through those two executions, then I don't see a reason why not.
Thanks.
Hi, thanks for the talk. So one nice thing about refinement types, as I like to view it, is like your presentation is sort of talking about how if you have a good implementation already, you can verify that it's good. But if you have like refined types, you can also use them to prevent you from having a bad implementation. So I'm wondering if there's a way to sort of extend the work that you did or modify it such that I can ensure that when I'm writing my data structure and the operations on them, that its amortized complexity is going to meet some sort of parameters.
Well, yes and no. So you, of course, can start a proof already if your data structure is not fully implemented. However, because once you have reflect a function into the logic of the SMT solver, you need to supply the proof. So what you would end up doing is basically jumping between your implementation and the proof and updating one at a time, which is probably not the most productive way to write code. So I think this is rather useful if you write it first, then see if it has the expected one, and then possibly go back to fix stuff. I don't think it works like the other way around easily.
Okay, thank you.
I just want to ask you a bit further about your time complexity function. You kind of implied that, at least by hand, you can systematically take any function and write a sort of time complexity version of it.
Yes.
Right. But isn't that a little tricky with involving laziness? If I just say, what is the time complexity of let x equal e in blah, right, then I can't just take the time to compute e, because that x might not be fully consumed by blah.
So
and it also depends even how much is consumed by the caller of this whole function.
Yep.
So it's a known, very tricky problem. So how does it work out so easily for you? It seems like magic.
No, so one thing is that you can just assume everything is evaluated, because we are only caring about upper bounds. So if you can prove it for these upper bounds, if you evaluate everything, then it will also hold for the lazy case.
That's a good point.
In many cases, you only care about single steps, which are by the definition you evaluate the single step, otherwise you wouldn't care about it. So usually that works out fine. And in fact, this even works out fine with higher order functions. So for the finger tree example that's in the paper, it uses, for the base cases, it uses fold L and fold R to fold cons and fold snock over the finger tree. And even then you can define a higher order timing function in the same way, and then have the proof work with that.
I see. So the short answer would be your systematic method just says this is going to give an upper bound, assuming strict evaluation, yes. Right? But your potential function, on the other hand, that's a purely creative thing.
Exactly.
The theorem prover, you have to come up with that out of whole cloth.
Yes.
That's not systematic at all.
No.
That's
basically the core of the proof.
That's creativity.
That's basically the one thing about the proof that you need to think about, because the rest of the proof is just showing that this function is indeed the correct potential.
Yeah. Okay, thank you.